All right, folks. So this week we're going to be talking about quantitative variables in lab. My guess is that your environment looks a lot like mine. It has a number of data sets loaded in, and maybe you have a bunch of files opened in your documents pane. So this is a good opportunity to clean things up a little bit. You can click this broom icon and it'll clear all the objects from your workspace. And this is fine to do. Everything that we need is in our R Markdown documents or in our code history. You can always click to look back through your history of code you've typed. So I'm going to click the broom. It says, are you sure you want to remove all objects? Yeah, I want to remove them. Then it cleans up my environment. And then I often will also go to File, and then something like close all or close all except current to close all my windows. So if I do close all, everything closes up there, and then I'd need to click on the quantitative variables pre-lab again to get it to open. And again, I can smoosh the edges of my panes around to give myself more room in one pane or another. So as always, we're starting by loading packages. You could remove this code comment and put in the other packages. Library, Mosaic. Oops, I suggested an extra M. I'll take that out. And then library, GG formula. Great. And then I could press the play button. And then maybe something will scroll by, maybe not if you already have them loaded in. And then we're going to load in my example data set. So we don't have it in our environment right now, so we definitely need to load the data in. And then in order for this R Markdown document to knit, we'd also need to have that code in there. So I like calling it GSS with a capital letters, but you could name it whatever you want as long as you use that name throughout your document. And then I'm going to put the assignment operator, which is the less than and then the dash, and then read.csv parentheses, and then quotation marks inside there. And then this is where I suggest you hit tab, and then it'll show you that there's a data folder. You could tab into that, and then you could tab to get the GSS clean. So your file path should look the same as mine, unless you uploaded your document to somewhere other than the pre-labs folder. Then we could hit play, and this is my same example data set that I'm always using. But this lab, we're going to focus on numeric variables, so things like number of children or age of respondent. So quantitative variables. So quantitative variables are those that encode a continuous numeric range with a bunch of possible values. So sometimes we'll talk about integer variables, which are just whole numbers like 1, 2, 3, 4, 1,000, a million. But we can also have more generic numeric type variables, which could have long decimals, like if you thought about pi, 3.141593, etc. So I think we've already looked for numeric variables or quantitative variables in this data set before, and there's quite a few of them in there. We can just kind of tell by looking at them in the data set previewer. So once again this week, we're going to be doing some exploratory data analysis, but in this case, we're going to be focusing on quantitative variables where we did categorical variables last week. We're going to do both elements of exploratory data analysis. We're going to do data visualization and we're going to do summary statistics. And we're going to start with the data visualization. So again, we're using the formula R syntax. We're going to have functions that start with GF for graphics formula. And then we're going to have an underscore and then the name of the plot we want to make. So in this case, if we're going to make a histogram, we would want to start with GF underscore histogram. And it's going to want a formula as its first argument. So this is going to be really similar to last week when we were making a bar chart where we're going to have just one variable. So we're going to start with a tilde, and then we're going to have the name of our variable. And in this case, I'm interested in number of hours worked last week. And I could click on my GSS data up here and scroll over and find that variable. Looks like there's number of hours worked last week. It's got underscores in the variable name. Some of these are NAs, 40 hours, 35 hours, 89 hours. That's a lot of hours. So I've got my tilde, my variable name, comma, data equal GSS, so that R knows where to look for that variable. And then I could hit the play button here, and then it's going to make a histogram for me. So here's a histogram of the distribution of the number of hours worked last week. I would guess that this big spike is at 40 hours because a lot of people work full-time and 40 hours is full-time. I'm also getting a warning from R. It's a warning message that says removed 967 rows containing non-finite values. And what that means is that it didn't have a value for that variable. It was an NA. I had 2,000 observations and almost 1,000 of them I didn't have a value for this variable. So maybe we shouldn't be making this kind of plot, or we should certainly at least be thinking some people didn't tell us how many hours they worked. Another thing that we should think about when we make a histogram is the bin width. So the bin width is how wide the bins in the histogram are. So if a bin is narrow, then we're just going to count up the number of people who are in a particularly narrow bin range of the data. But we could add another argument to our GF histogram function. So arguments are separated with commas, so we could add a comma after data equal GSS, and then say bin width is equal to, for example, 10. And if I hit the play button, there is a histogram with a bin width of 10. So these bins are 10 wide, so this is the very spiky middle of the people who worked around 40 hours. So I'd like you to try adjusting the bin width, change this number, and see if you can find an appropriate bin width, what you think is appropriate for the data, and then you could come back. All right, so this is one of those things that's more of an art than a science. So there's not a correct answer and an incorrect answer. You could try a bin width of 15 hours. That makes it even more blocky. Maybe you could drop it down to a bin of 5 hours. I don't think you'd want to go down as low as 1 hour because that's so spiky. Although it lets you see a lot of people reported working 40 hours a week, more than 400 of them. Some people report working 50 hours a week. I would guess that this is a spike at 60. So probably the spikes are at sort of common round numbers. And I think this is probably the person who said that they worked 89 hours is way out here. So I really think that a bigger bin width, like 15 or 10, that's probably better. But it kind of depends on what you want to say with your data. So now that we've made a histogram of the number of hours worked last week, I'd like you to make a histogram of the numbers of brothers and sisters variable and pick the appropriate bin width. So again, I'd encourage you to pause the video here, try making your own histogram, and then come back. Okay, now I'm gonna do it. So I'm gonna delete this code comment that says write code here, and then I'm gonna start typing my code. So I'm going to use the GF underscore histogram again, and then parentheses. And then I need a tilde and the name of the variable that I want to visualize. So in this case, it's number underscore of underscore brothers underscore and underscore sisters, comma, data is equal to GSS. And then I could hit the play button. This is interesting. I think this really shows me this is a skewed data set, and it is right skewed because the tail goes off to the right. So it's showing us that, most people have just a couple siblings, but then there's this long tail where people have, 20 plus brothers and sisters. So we might want to change our bin width. Let's say bin width is equal to 5, and let's try that out. Okay, I think that's too blocky. So this is showing people who have 0 to 5 siblings, and then 5 to 10, 10 to 15, that kind of thing. We could try bin width of 2. Maybe that's better. This is something that's integer, so I think that a bin width of 1 could actually work here if we wanted to do that. But I think no matter what bin width you pick, you can tell that it is a skewed distribution. So now we've made a histogram of a couple different variables. We're going to try making a density plot instead. And the question is, what GF underscore function do we think is going to do that? So I would encourage you to try hitting GF and then a tab, and then use your arrow keys to scroll through the GFs and see if you can guess which GF function we want to make a density plot. There's lots of GF functions, but I think GF density is probably a good guess. So I'm going to hit tab, and then I'm just going to do the same code that I'd done before. I could actually copy it if I wanted to. I don't know if that bin width is going to be relevant for the density, but we could try hitting the play button. And let's just take that out, see if that makes a difference. I don't think that the density plot has a bin width argument. But the density plot is more a smoothed density, which is going to show us the distribution, but in a little bit different way. And then the last thing we're going to do is we're going to make a box plot. And I'm guessing that you can figure out what GF function we want here. So why don't you pause the video and try and make a box plot of that same variable. Okay, so we're going to do a GF underscore box plot and a tilde and then number of brothers and sisters, comma data is equal to GSS. You could hit the play button. And this makes a box plot. So we can see the median, that's the middle of the box here. We can see the edges of the Q1 and Q3. We can see the whiskers, and then these are all the outliers. So if you have 10 brothers and sisters, you're an outlier in this data set. My dad was one of 13 kids, so I think that he would be an outlier in this data set, but he's certainly not the biggest outlier. Some of these people had 25 brothers and sisters. And I would be down in the main part of the distribution. I have one sibling. So again, we can kind of see the same skew in the data set, but the box plot is kind of looking at it in a different way. So that was visualization for one quantitative variable, but there's another type of visualization that we might want to make, which shows the relationship between a quantitative variable and a categorical variable. And if we want to make that kind of visualization, one way to do it is with a side-by-side box plot. So we want box plots side by side for each of a number of categories. So we're going to use the y tilde x syntax because we're going to have two variables. And I'm going to try and make separate box plots for the number of hours worked last week variable based on the levels of the marital status. That's the categorical variable. And I would just encourage you, again, to pause the video and see if you can figure out how to make that code work. All right, I'm going to do it. So I'm going to do a GF underscore box plot. So it's the same function. But now I'm going to have y tilde x. And I'm going to do number underscore of underscore hours worked last week tilde marital status. And then, of course, I need comma data is equal to GSS. So let's see how that worked out. All right, so this made me a box plot, and I could smoosh it out so it's a little bit easier for me to see. It looks like people who are divorced and married maybe work about the same amount. There's more outliers on the low end for married people than there are for divorced people. We've got separated people, they're maybe working a little bit more. Their box is kind of going up higher. Widowed people, maybe on average, or sort of the median is the same, but then they tend to have a distribution that skews lower. And that kind of makes sense to me. Widowed people are more likely to be older people. Probably that means they're more likely to be retired or working fewer hours. So I think that this plot makes sense to me. And then let's just see what it would have looked like if we had flipped the variables and done it the other way around. So I could take this off, and then it'll be marital status tilde, and then the number of hours worked last week. If I hit the play button, now I get box plots, and I guess they're not exactly side by side, they're kind of on top of one another, but it's the same box plots. And it lets me see about the same information. So does this plot make sense? Yes. The medians are about the same, but it looks like widowed people work a little less. I think that makes sense to me. So one note is that you can only make side-by-side box plots if the variable you're using to split your data is categorical. And R uses this term of factor for its categorical variables. So if R thinks your variable is not categorical, you might get an error or you might get a really weird plot. And if that happens, you might need to wrap the factorize function around your variable. So mine worked the way that it was, but if I had been having trouble with my marital status variable, I could have put factorize around that marital status variable, and that might have fixed my issue. So if you have a categorical variable which has like a 0 and a 1 as the levels, R might think that that's a number, and so you might need to wrap factorize around the name of that variable. In this case, it's not actually going to change anything. And so in this case, nothing. But if it was a binary variable with 0, 1, it might have fixed a weird plot. Okay, so that was data visualization for quantitative variables. First, we talked about data visualization for one quantitative variable, and then we talked about visualization for a quantitative variable and a categorical variable.